This video is for Chapter 12, Tests of Statistical Significance for PSY 222, Research Methods in the Psychological Sciences. This chapter starts by exploring what's called confirmatory data analysis. Just to review kind of where we're at in your journey through research methods this semester, you've learned here in the last section of the course that there are three major stages to the process of data analysis: familiarizing yourself with the data, summarizing the descriptive statistics, and in some cases providing visual ways of imagining the data, and then confirming what the data tell us by conducting tests. Right now in your semester project, you're at the stage of actually running your data so that you can summarize it and so that you can actually conduct tests such as t-tests and analysis of variance tests to confirm what the data tell you and decide whether or not there is support in the data for your hypotheses. In this final stage, what you're doing is deciding, as I just described, you have hypotheses, and in your semester project, I've worked with you to articulate hypotheses that go with the data set that we have, such as, there could be a difference based on age in scores on perceived stress scales. And maybe you predict that people who are in their youth have more stress or report more stress than people who are older than them. And what you would be predicting is differences in means, so higher perceived stress scores among the young versus the older people in the population. In the final stage of data analysis, you're evaluating whether or not the pattern in the actual data you have supports your claim, supports your hypothesis. One way of putting that is to say, based on the data I have, what can I say about my behavior of interest? For example, perceived stress scores or optimism scores or self-esteem scores. Sometimes we call this stage confirmatory data analysis. The most common way of doing that is by doing something called null hypothesis significance testing, or NHST. With null hypothesis significance testing, and I will say that the NHST approach has become more controversial in recent years, and that's what has been kind of driving the call for researchers to report things like effect sizes and power analyses and confidence intervals, in addition to NHST information such as p-values, because there are limitations to the NHST approach. That said, you need to understand what NHST is, because when you read journal articles, even if you go on in the rest of your life after college and become a counselor, when you read journal articles and you're given significance test results, you need to understand how those results are arrived at and what is the appropriate way to interpret them. The goal of NHST is to decide, for example, if the mean differences that you see between groups, so let's say that I do see a higher mean perceived stress score among the youngest participants than I see among the oldest participants in our data set. How do I decide? Is it a big enough difference that it's meaningful? And as your authors put it, are the differences among the groups big enough, or are they just due to chance or what's called error variation? The first step is to start with the assumption that there aren't any differences between the groups. In other words, the independent variable, or if I'm looking at my natural groups design in our data set, that the variable of age divided by groups doesn't have an effect on, say, perceived stress or optimism, for example. Then you use probability theory. Actually, it's mathematicians who created a system for using probability to estimate how likely it is that the results you actually got are going to, be produced by mistake through error. The significance test itself, when we describe a result as statistically significant, what you're assuming and what you're trying to demonstrate using NHST is that there's a small likelihood, but tolerable likelihood, that you're going to find this pattern of results even if there's actually no effect. So, try and be patient with your brain as you process that if this is the first time you've really given much thought to a null hypothesis significance testing. So we go in as the scientist saying, there's nothing here. I may see that one group's mean is higher than the other group's mean, but my assumption, and I'm going to put it up against probability theory to decide whether the pattern I'm seeing right now should be declared statistically significant. Since what we're doing, we're making decisions. So as the researcher, you have to make, based on the probabilities, a choice of whether you're going to say the no effect assumption, the no difference between means assumption, I'm going to declare that that's not the case based on the data that I have. So you have to accept that there are certain kinds of errors that might happen. You may reject a true null hypothesis. So you could say, yeah, there's a mean difference and it's something I need to interpret. That would be a type 1 error where you're rejecting a true null, where there actually isn't a reliable mean difference. It's just an error due to error variation in my sample. The other type of error is when there was an effect, but you have not detected it. So there was a difference between means. You could see it in the means, but you state that it's not reliable enough for you to interpret it. That's a type 2 error. The steps involved in NHST, first, as I've already said, you assume that there are no differences between the groups. The null makes the assumption, therefore, that the independent variable or the grouping variable didn't have an impact on the dependent variable, the measure of behavior that you're interested in. The second step is to actually compute the proper statistic. So if you're comparing two independent groups, you use a t-test. If you're comparing, use an independent samples t-test. If you're looking at dependent groups, you use a dependent samples t-test. If you're looking at 3 or more groups and comparing them, you use analysis of variance. If you have participants completing tests at multiple points in time, that's a repeated measures test. And then there are all kinds of non-parametric alternatives to those tests as well. Each of them has a statistic and a distribution of those statistics and a way of determining, based on probability theory, the probability values, or p-values, that determine statistical significance. You want when you say that a result is statistically significant, you want to assume that there's a small likelihood of that event actually occurring when the null is true. So you want to have a rigid test. You want enough of an effect that, and you're being conservative in deciding to accept that result for interpretation. If we reject the null and we are then giving ourselves the ability to conclude that our independent variable had an impact, or in other words, if you're comparing groups, that there are mean differences that are interpretable, then if you describe that, then you're taking into consideration that there's a certain probability of type 1 errors and a certain probability of type 2 errors. So when we ask the question, like this adorable golden retriever asks, is that test statistically significant? You should be asking the question, what does this outcome tell us? And this is where, a lot of times students say, I am not going to be a researcher. Why do I have to learn this? Well, because even if you don't become a professional psychologist or a counselor or a social worker, and you never read a scientific journal again in your life, you will read news reports about research. And sometimes those reports will include information about statistical significance. It's important for you to be a smart consumer of scientific information. So when we ask the question, what does a statistically significant outcome tell us? The way you think about it is the smaller the exact probability, and this is the statement from your text, the smaller the exact probability of the outcome that you've observed, the greater the likelihood of an exact replication of your study will produce a statistically significant finding. Now, the wording is really important there, an exact replication. So you have to kind of use your imagination and say, okay, I did this study, I'm looking at the results, I've got a statistically significant result. The probability, the p-value that you're looking at, when you interpret that appropriately, it tells you how many times, roughly speaking, if there was an exact replication of this study, how many times out of 100 would I make a mistake in concluding there was an effect? And generally speaking, we want to tolerate only a 5% error rate. So the smaller the exact probability of our finding, so let's say you get a t-test result and it's significant at the 0.05 level, meaning your p-value was less than 0.05. The smaller that number, that p-value number, the greater the likelihood you're going to get the same finding if you did an exact recreation of the study. Now, the APA in recent years has moved in the direction, and in the most recent version of the publication manual, the guidelines are pretty clear. They want us to report, since statistical packages like SPSS, they give you exact p-value numbers. You probably get sick of me saying it, but when I was taught statistics, we had to look everything up in a table of values for every test that we ran. And what was the convention in reporting in journals was to just say that if you got a significant result, you reported p less than 0.05. Now, stats packages give us exact values of p. Unless they say you're looking at your SPSS output, it says p equals 0.000. Unless it says that, you're to give the exact value of p. If it says 0.000, there's actually a number there somewhere, but it's out too many decimal points for the printout to give it to you. So what they suggest then is that you say p less than 0.001. And just leave it at that, and then your reader knows how to interpret that properly. With NHST, there are a couple of possible conclusions, as your authors state. You're either going to reject the null, or you're going to fail to reject it. And I want you to absorb that sentence. There's a lot of the logic here, and I remember trying to learn this as a student and finding my head just starting to hurt. Even though it seems deceptively straightforward, but I see this mistake even in published journal articles pretty often. When you're doing probability, when you're talking about the likelihood of making type 1 and type 2 errors, it's important that you get the logic right. So when you're making these statistical decisions about significance, you're either going to reject the null, i.e. the no effect, or you're going to fail to reject it. You're not going to accept it. You're not going to say it's true. You're just going to fail to reject it. what we conclude is that if a finding is not statistically significant, we have to be careful in the way we interpret that. We don't just say, "Oh, no difference." We don't accept the null hypothesis and then conclude that the IV didn't produce an effect, or that the mean scores for the groups were not different, because the mean scores are the mean scores. What we at the end of the day, you can't make a conclusion about effects based on a single finding, because there could be other factors that are preventing us from seeing a difference. So there could have been intervening variables, there could have been confounds, there could be simple things like problems with instructions, or some of those threats to internal validity that you learned about in previous chapters. It could also be that your sample size was just too small. There are a whole host of reasons why an effect may not be able to rise to the level of statistical significance. So we don't just say, yep, null hypothesis is true. The convention is to say that you failed to reject the null hypothesis. Now, I copied this image from your text. This is a handy way of visualizing the difference between type 1 and type 2 errors. I tend to, just to keep things clear in my mind, I try to think about it in terms of differences between groups, so that I have an anchor somehow for thinking about these two different types of error. So when we say the null hypothesis is true, what we're suggesting is that that's a result where you do not see a significant difference between the groups. What if an exact replication were done and you actually find that there is a difference? That would be a type 1 error. So in my current outcome, if the null hypothesis is true, and I declare that there were differences between the groups, I've made a type 1 error in that case. If, however, the null is false and there are differences between groups, and I reject the null hypothesis, I've made the right choice. If I reject the null hypothesis when the null hypothesis is actually true, meaning that there are no meaningful differences between the groups, then I've committed a type 1 error. If I fail to reject the null hypothesis, and if you imagine that in terms of between groups differences, if I fail to reject the null and the null is actually false, meaning there were differences to be detected, that's when I've made a type 2 error. If the null was true, then I've made the right choice. So to pull some threads together here, the type 1 error is rejecting the null when it's true. The probability of making a type 1 error, because you want to limit that. You want to be able to actually detect differences, but you don't want to make false claims that differences are significant. So what we tend to do is adopt a fairly restrictive level for declaring significance. Now you could make it more conservative by having, instead of a 0.05 level of significance, you could select a 0.01 level of significance. The problem, though, is if you just adopt a more conservative significance bar, a significance value, then that is going to drive up your possibility of making a 2-1 error, which is missing an effect that was real. And it's always a trade-off. It's always a balancing act. And part of why it's important for you to understand how NHST works and about the difference between type 1 and type 2 errors is that you need to be having these thoughts when you read about researchers' findings, because you have to understand that a finding in an individual study is a finding in an individual study. It's not that it's meaningless, it's just that it needs to be carefully interpreted in the broader context of how these statistical decisions are made. And that leads us to, why do we, meaning scientists, including psychologists, why don't we use the word prove? And you may have noticed, some of you in your homeworks, in your worksheets for your semester project, if you started trotting out the word prove, I'm going to tell you to stop. I'm going to X that out and replace it with some other wording. We don't use the word prove. What we are doing is estimating probabilities. We're not proving truth and falseness. And scientists have a culture that values the accumulation of evidence to support hypotheses and eventually theories. We are very careful about words like proof. Instead of saying prove, what we do is say things such as, the findings were consistent with the hypothesis, or the findings confirmed the hypothesis, or the findings support the hypothesis. And sometimes with my student researchers in the SCE, they find this language just not satisfying. You know, you've gone to all this work, you've collected this data, you've found a significant result, and it supports your hypotheses. Why can't I just say my hypothesis was proven true? Well, it's a culture thing, but it's also just a more accurate way of acknowledging that when you're doing NHST, you're estimating the likelihood of type 1 and type 2 errors, and you're making a judgment. That judgment is always going to be open to error and therefore open to interpretation. So what we do in our language, in the way we describe our results, is we talk about consistency with hypotheses or support for hypotheses, rather than the very value-laden and heavy word of prove. This difficulty of accepting the fact that we may not be right when we make a judgment about the null hypothesis, it should be a powerful reminder that single studies really tell us relatively little about any given behavior of interest. What is powerful is replication and the use of multiple methods. Science really doesn't advance on a single finding, and it shouldn't, because there are just too many errors that are possible in any single finding. Just to give you a simple example, I collected some pilot data last year, actually it was 2 years ago, and found some really tantalizing, interesting findings. It was a small pilot, about 30 subjects, and they weren't carefully chosen. They were seriously a convenience sample. When we collected more data under more rigorous sampling procedures, it was found that the effect was simply not present. That kind of process is how normal science should work. If you have a suspicion, a hypothesis, you need to test it. You're not done with one-shot deals. You have to replicate yourself, and you also have to submit your work to the scrutiny of others, and value the process of multiple replications using multiple methods. Your authors talk about, and I mentioned earlier, it's starting to become more normative in psychological science to report measures such as sensitivity and power when we report our results. It's not completely ingrained yet, but it's getting to be more common. When we talk about the sensitivity of measures or the sensitivity of a design or a result, what we're referring to is the ability to find an effect, to detect an effect. What that's suggesting is the way you've done the manipulation of an independent variable, for example, has made it likely that you will detect a finding if it's there to be detected. Power, on the other hand, is the likelihood, as your authors put it, that your result is going to allow you to reject the null correctly. And we have to pay attention to both these things. We want our measures and our methods and our designs to be sensitive enough to detect a finding. We also want enough what's called statistical power to be able to be confident in our decisions to reject the null. The power of a test is going to be dependent on, in part, two things. The size of the effect. So if you're looking at comparing means, how large is the difference between the means? And then also the sample size. So a lot of the calculations that you can do to determine the power of your particular test with your study is going to be a combination of these two things, the size of the effect and the size of your sample. That's why, one of the ways that we increase statistical power is to have a bigger sample. It helps to establish greater reliability in the finding that you have. Another issue, repeated measures designs, and you learned a bit about this in your Pallant homework. Repeated measures design do tend to be more likely to pop results and to have more power than independent groups designs, because you're having the same people serving as their own controls. You can maximize the power of your number of subjects by having them complete measures in more than one condition. That controls for more of the error possibilities and the individual difference issues. As your authors put it, these repeated measures designs have more sensitivity and more power because your estimates, your statement about how much error variation there's likely to be, it's likely to be smaller. Mostly because you are controlling for those random individual differences that could happen when you're assigning people to groups. Type 2 errors have been argued to be more common in psychological research than are type 1 errors. So that's a difficulty, and we need to keep it in mind. It suggests that we need to think harder about what we're willing to tolerate and what we're not willing to tolerate in our research, and it should be corrected for. When we have results that, sorry for the typo there, that is supposed to be a greater than sign. So when results are not statistically significant, you shouldn't conclude that the null is true. Instead, you've failed to reject the null. Since we're more likely to make these type 2 errors, we have to be careful with our language so that we're clear. We're not saying there's never an effect or there's no effect. What we're saying is that we failed to find a result that helps us to reject the null hypothesis. And that concludes part 1.